Before moving into convolutional neural network, first let's understand artificial neural network. This artificial neural network has been around from a long time, like some 1600s or something, but it was very difficult to train it, and mainly because of this issue of vanishing or exploding gradients. So we'll come to that later. So in this right side, we can see this is a typical neural network. So this is inspired from our brain, or we have neurons in our brain, and that's how this architecture was inspired. This neuron got inspired from our brain only. So yeah, so this is the crux of it. This is where it all starts. So like we created one network or one architecture in which we will take an input as one-dimensional array, and this one-dimensional array will be given to neurons, and these neurons is nothing but this. Just multiply each weight with multiply each input with a weight, and sum it up, and then add a bias value. So numerically, for example, let's say we started with random weights, let's say 0.5, 0.3, 0.2, 0.5, and the inputs are, let's say, some like it can be anything, like maybe an image, two-dimensional image serialized into one-dimensional data, or it can be audio data. But typically in neural networks we will not use raw data directly, we will use features only. So let's say for the image we found some histogram, and that histogram data we will be giving as input here. Or for audio, it's DCT coefficients can be calculated, and maybe that is what we will be providing here. So some inputs, let's say 0.3, again 0.2, 0.2, and 0.1. So those are the inputs. Then these 0.3, 0.2, these values will be multiplied by these weights, and this dot product, basically multiplication and addition. That is sigma wi(xi) will be done, and then plus a DC term. So that is what is this bias called. It's a typical filter structure, like these are filter coefficients and these are inputs, and after multiplying we need to add a DC coefficient such that that filtered thing is shifted upwards or downwards as required. So that happens in here, and then that is given to an activation function. The activation function is a non-linearity function. Basically, the sigma wi(xi) plus b0 will be given to a function f of x. That function f of x is f of x will apply, like example, the sigmoid is the most common non-linearity function, and s-shaped function, maximum 1, minimum 0, and it's not linear. S shape will be there. So the requirement or need for this is to bring in non-linearity by making this neuron output non-linear with respect to input, and then when we add multiple such neurons, the complexity of this combined, like here some non-linearity is there, like and here also non-linearity is there. So these non-linearities are given to next neuron. It will again do this weighted sum, weight multiplication and addition and bias addition, and then again another non-linearity here again. So like it becomes even more complex, and so this way we will make our that will make our neural network highly non-linear structure, and the advantage is it can learn complex patterns because it's a complex model. So if it's a really simple without non-linearity, another thing is like we can, like if we can compress them into a single hidden layer. The effect of having multiple this kind of neurons will go away if there is no non-linearity. So yeah. Now it is as simple as that. Like have these neurons connected, and this is the very beginning initial architecture in which each neuron is connected to every other neuron or to all the entire input. So that's how it was in the beginning, and this is what we called ANN, or artificial neural network. Things have changed in the convolutional neural network. Mainly this taking each neuron taking the entire input. That was the big mistake, and that is fixed in CNN. We'll come to know in the next session. So here one more thing is needed. So we talked about these weights. Now let's say we are giving cat image here, or features of cat image, and this neuron is supposed to predict like as 1 here and 0 here, and next we are giving a dog image features here, and then we are expecting here it to be 1 and here to be 0. So that is our expectation. That is what we need this network to learn to differentiate between cat and dog. But to achieve this, a set of certain weights are required. So we will start with a random weight, and we will just give this feature, cat image feature as input. It might predict like 0.5, 0.5 typically, or some random value, like maybe 1.3 and minus 1.3 or something. So that value range is determined by the nonlinearity function. Here sigmoid is there, then output will be only between +1 and -1. Here also +1 and -1. So yeah. Okay, so let's say we got it as 0.5, 0.5 or 0.3, 0.4, something like that. So it is not the expected output. We want, when cat is given, we want here to be 1 and here to be 0. So how would we how will we find the weights such that we get the expected output, or at least close to expected output? Like 1 and 0 is expected, 0.9 and 0.1 is coming, then that is also okay. We can just take a max of, easily find out like which one is bigger and take the output. So that is where this back propagation comes into picture.